Welcome to another exciting edition of the CG Shading Series. This is Nate Nestler for Hyperactive Studios, and we're covering the whole Phong shader. We're getting into Vertex lighting with textures this time. So we're just going to keep it simple on this. You can get fancier and actually have a texture for the specular too. However, we're just going to do only a texture for the diffuse area for the most part, for the overall model. So we're going to continue on building off of what we're kind of working off from before, and then we'll move into our Phong texture pixel shader lighting using Vertex also, but not for the lighting aspect. Okay, so we have the same setup. If you want to, you can just go over here and copy and paste your code from the one from the previous video, and then go ahead and go here, create effect here, and then name it Phong texture, and choose empty, of course. Phong texture Vertex for the name. Alright, and then paste it in. And when you paste it in, you'll get this exact same setup here throughout all this here. And none of this has changed. This is all the same. Here's a place where something has changed. Right here. Now you're going to add float2 space UV here, colon, text chord 0, that's a 0, semicolon, and that's going to be the texture coordinate, first set of texture coordinates, and we're going to be applying the UVs to that. Then under VS out here, we're going to have not just our position here, but we're also going to have a UV for this one also. And this is where you're going to see something a little different. You're going to see where we've changed some things. We no longer have outputting color here. We're actually outputting diffuse and specular here separately, and they're all float. This is a float 2 for our UVs here, and it's still going to be colon, text chord 0, semicolon for our first texture coordinate space. Then we're going to do a float 3 here for a 3D texture coordinate space here, and then we're going to do diffuse, and then we're going to do colon here, text chord 1, semicolon, and then we're going to do another one here, float 3 specular colon text chord 2, semicolon. Okay, so you've probably never seen this before. Basically, this is the method in which we need to get our values from, for instance, from our Vertex shader into our pixel shader, and we cannot pass them directly. There's no way to do it, I'm afraid. So the only way to do it is to pass it through texture coordinates. So that's what we're doing here. We're passing it through the texture coordinate systems, and in order to pass these values over, and we're shading them per pixel, per vertex anyhow. And it's getting passed in, and then we can manipulate that as texture coordinates, like an image, in the pixel shader. And so that works as a compatibility bridge between the Vertex and pixel shader for that setup there. And then on the struct, of course, we're doing the same thing as always here. Struct FS out here, open curly brace here, float 4 color, colon, color, semicolon, close curly brace, semicolon. So nothing new there. But yeah, so that's how you're going to have your VS out or Vertex shader out. Alright? Don't forget these are curly braces here. And then a semicolon terminates the set of curly braces for a struct. And don't forget that. Alright. So here we go over to the artist's tweakable parameters. Great. So here we have our ambient light, and we have our global ambient just as before. Nothing new there. We've got our KA here, and our KD, and our KS, and that's all the same. Nothing's changed. Scrolling on down, our spec power, our specular power, nothing's changed there either. That should be the same also. The same thing goes for our point light lamp here. That should be the same all the way throughout on that also. Then we get to our color and texture, and it's the same color and texture setup we've been using for I don't know how many shaders here in videos, but continue on with that same setup. Here we go. Texture here is a special qualified name that we have to use, and then the name of our texture. In this case, I'm calling it color texture here. We're going to start it up with a opening less than sign, string space resource name, capital R, capital N, everything lowercase, equals, in quotes, default underscore color dot DDS, close quotes, semicolon. Remember, this is a texture that comes with FX Composer 2.5 stored in a special folder with the other textures, so it automatically knows where this is, so don't worry about that. string space UI name, capital UIN with the lowercase AME, equals, in quotes, diffuse space texture, close quotes, semicolon, and this names it right here. So we're naming on the UI what this particular thing is. So if I select this real quick, and we have this set up here, you can see that diffuse texture is the name indeed that goes here, and this one could select a different texture to be loaded onto this model. Excellent. And of course it's going to be mapped according to the UVs of the model, which we're passing in from the actual model itself from the 3D program, like OpenGL or DirectX. Okay. In this case OpenGL, since we have it set to OpenGL. Alright, so with that we're going to say string resource type equals, in quotes, 2D semicolon. This is a 2D texture. We need to notify to FX Composer that we are working with a 2D image, and it needs to be mapped accordingly. Close greater than sign, semicolon. And then we're going over here to our next part here, sampler 2D. Now remember, sampler, that's going to be accessing each vertex or pixel, oh, not each vertex, sorry, each pixel or fragment, I just want to call it computed pixel, on the actual image to be simultaneously computed across all the different parts of the 3D card. So again, that's what's involved there. So so we have to set up a sampler to handle that aspect. So sampler 2D space color sampler equals sampler underscore state here, and then open curly brace, then texture equals what texture we're using. So open greater than less than signs, we're going to have color texture in there, and that's not just some special name, that is literally the name of the texture we set up over here. Semicolon here, min filter equals linear map linear semicolon, camel casing it here for the capitalization here. Mag filter, that is a mag filter, don't forget that, equals linear semicolon. Then wrap s here, because we're going to have s and t replace our u and v to be mathematically manipulated, in this case repeated, equals repeat semicolon, and then wrap t equals repeat semicolon, close curly brace semicolon. Alright, vs out space main vs open parentheses vs in space capital in close parentheses, and we're going to have a return type of our struct here for our vs out. Okay, so we have our vs out here. Now don't forget, this lets us come back up here and we can see our vs out here, and that has our position, our UV, our diffuse, and our specular parts that we're going to be exporting from there. And then we have our vs in, and don't forget, if you come back up here to your in, this is going to be our position, our normal, and our UV that we're going to be passing in, okay, to our shader for our structure. Alright, and this is that's the return type, of course, for the for the function. Alright, so open curly brace here, and then we have a vs out for our struct here we just showed you a second ago here, and all capital OUT semicolon here for our out variable. And again, this is done to make it easy to tell what's coming in and out of the shader. Alright, so float 4 here, PO for object position here for that point here equals float 4 open parentheses in dot position comma 1.0 close parentheses semicolon, and of course that's to make what? Homogeneous coordinate system here for our object position in object space, our position of our point in object space. There we go. Alright, so here our PW, our point in world space coordinates, is equal to the multiplication of our world space matrix times our point position in object space. And then we're going to return with XYZ dropping off the homogeneous W coordinate. Alright, so here we go, float 3 here and in normal. And again, I like to do my in right here for my normalize on this, and it's equal to the multiplication of the inverse transpose matrix times our normal in object space, and then that'll convert it into world space coordinates. And we're going to have it in non-homogeneous coordinates by having it in .xyz, and then it'll be normalized, of course. So we'll just get just the direction with none of the magnitude. We're also going to normalize our L vector. Remember, L vector goes what? Points back to the light. Remember, our N vector is our normal vector, which points straight up. So L vector here points to the light. It's good old light right here. And our N vector goes straight up. Awesome. Okay, so with that, what we're going to do is take our lamp position, or shall we say our light position for our first light here, subtract that from our point world space coordinates. So our point in world space based off world space coordinate setup,
subtract it from that, and then we're going to normalize that in order to get our direction to our light from our point in world space coordinates. And it's going to be normalized, of course, no magnitude. Okay, so we're going to do float 3v here, and v is going to be our view, or our camera, or the eye, or whatever you want to call it. It's going to be normalized. It's going to be equal to normalized, and we're going to say float 3 here, and we're going to say what? We're going to say view ix. Now remember, the view here is our inverse view matrix, and we're accessing what? We're accessing the transform tx, ty, tz. If you don't remember from previously, I showed this before, tx, and we're accessing the first row here for the matrix, not matrix, well it is a matrix, but array matrix row 0, and then w, which means w is going to be the tx, and then we're going to hit up what? We're going to hit up the, and so that covers this one. That's what the 0 is that first row. The w here again is that tx, and then we're going to hit row 1 thereafter, and then row 2. And remember, on this case it's going to be ty and tz, and I'll show that real quick. We're here. Here's the ty with row 1 here, which is the second row, and then row 2, which is the third row here, tz. And again, that's because we start counting from 0. This is the 0 row here. Okay, very cool. Computer always starts counting from 0. Alright, if you're not familiar with that, that's what's going on. Alright, so here P for our point on our model here in world space coordinates, subtracted from that, basically our vector that's generated from grabbing those particular points for the transform matrix transforms. Alright, for tx, ty, tz. And then that gets normalized for the view. Alright, cool. Let's calculate our r here. And I'm going to call it rn real quick for my r normalized. I'm going to say float 3 here, rn equals normalized, open parentheses l plus v, close parentheses, semicolon here. And that's going to let us add together the normalized l and the normalized v together. So that way they're normalized, but their resultant is going to be larger than what we're going to be within a 0 to 1 relationship here for the magnitude of the vector. So therefore it has to be normalized to get it back into a 0 to 1 so that we don't end up scaling our calculations, and that's an undesired thing. We only want the direction. So again, normalize to get the direction and lose all of the magnitude of a vector, the length of the vector, if you will. Alright, so float 4 here, lit v equals lit. Don't forget the lit function. What does it do? Well, real quick, what it does is lets you pass in our n.l for our diffuse and our n.h, or in this case n.r for our specular, and then pass in our specular shininess value here. Alright, that's what that does. And then it comes back with what? For our y value here on the vec 4, our 4 float vector, our y value here is going to be what? The diffuse, and our z value is going to be our specular. Alright, and again, if it goes below 0 on the diffuse or for the specular, it's going to come back to 0, automatically be set back to that. Awesome, so that keeps us from having to write an if-then condition statement. That's how we avoided that. Okay, so it just simplifies things, basically. Okay, so here we have our float 4 here. Lit v equals lit here, and in parentheses, dot, in parentheses, l, comma, n, close parentheses, comma, dot, open parentheses, r, and this should be n. And again, all these are going to be normalized. So this will be ln here, this will be nn. N for normalized normal here, ln for our light vector here that's been normalized, rm for our reflection vector, nn again for our normalized normal, and then we have our specular power. Awesome. We have the specular power. Alright, so from here we go on down to our ambient equals lit v dot, well, it doesn't have to be lit v dot x. Matter of fact, it's faster if we don't have that in there. Just, I guess I have it. Alright, so Ka here is going to be what? It's going to be our ambient artist controllable value right here for our color. There it is. That is Ka. Don't forget, times our global ambient. Our global ambient is our ambient shadow one over here. Right? That is our ambient shadow. A little more realistic than just total black pitch darkness on that. Okay. Which is a wonderful control to have for the artist. Alright, so moving on, we have our float 3 here, diffuse equals lit v dot y. What's dot y? Dot y is diffuse. That's right, that's our diffuse intensity value for that particular point on the model. All right, times lamp, well, basically our light color from our light here in the scene. Okay, next one. Float 3 specular equals lit v dot y. Remember, lit v dot y is what? The diffuse power times lit v dot z, which is going to be our specular power here, or our specular intensity for that particular point on the model. Diffuse intensity for that particular point on the model. Times our ks. What's ks? Which is our specular color here. R is definable. Yes, awesome. Alright. And there's that right there. Times our light color, basically. Alright, all that together makes up our specular. Awesome. So now we need to get this out of this particular vertex shader, because we calculate this per point, which is going to make it very efficient. However, it's not going to be exactly what we're looking for here right now. So this is applied, but you can kind of see it's a little harder to tell with the texture on it, but this is not the smoothest specular on it, because we are still using a vertex lighting here for our Phong texture setup here. But we're going to be moving this out now, out of this particular scenario. So final color and position here. Out.diffuse equals diffuse plus ambient. Right? Figures out our diffuse particular setup here. Specular equals specular plus kd.rgb. Awesome. And then position is equal to multiplying the world view projection matrix times our float 4 here. Now you remember we can just replace this with our PO here. PO, like so. Now you should already have this from before, so make life a little easier for you. And then we're also going to pass through our UVs too. Of course, again, they're going to have to get into what? The PS shader here. Alright, so it's out.uv equals in.uv semicolon here. And then we're going to return out semicolon. Close curly brace here, and then we're going to open up with what? FS out. FS out is what? Our fragment shader output, which is just going to be the color only here for our struct here. And we're going to be passing into this thing, this whole thing right here for our vertex out. Remember, what we pass out of the vertex shader is what we need to pass into the pixel shader, or our fragment shader, however you want to call it. And that is going on right here, and that's what we're passing in. And we're calling the variable in to let us know that, hey, this is in, this is coming in. FS out here, space capital out, right here, semicolon. This lets us know that, hey, it's coming out of the shader here. Alright, awesome. So now we have our float 4 here, diffuse equals float 4 in parentheses in.diffuse.rgb comma 0.1 f. Close parentheses, semicolon, to give us what? Homogeneous coordinates from our non-homogeneous coordinates for the diffuse. Same thing for specular. Float 4 here, specular equals float 4, open parentheses, in dot specular here, comma 1.0 f, close parentheses, semicolon, and that gives us our homogeneous coordinates versus our non-homogeneous coordinates. All right, very cool. All right, so out.color equals open parentheses diffuse times text 2D open parentheses color sampler comma in dot uv, and this axis is what? This axis is all the little points, pixels if you will, on our texture to be simultaneously computed across the shader, and we're multiplying those together. And then we're going to multiply it times our specular in order to get the right look to it. It just looks the best if you do it with the multiplication here on the specular. I know typically you're supposed to add this stuff together, but actually multiplication works out better for this right here for our out color. Then we're going to do return out right here, and then close curly brace. Okay, and that is going to give us a specular vertex shader here, Phong, with texture capability. And the only thing we have left to do here is go to our technique. And we do have to add our fragment program here, which is going to be fragment program equals compile space fp40 and space main ps open close parentheses semicolon. And we could probably get away with a really low number here if we wanted to. I'll double check it real quick. And no, we can't. Oh, it would so help if I did that right? Alright, so that's not going to work. What if we did it with 30? we might be going outside the realm of what we're allowed to do. Oh, we're going to probably go 40, it looks like. Did I accidentally delete? Hold on. Yeah, okay, so it does work on 20. I just accidentally deleted something I didn't mean to. Okay, there we go. So it works all the way back to 20. Awesome. But I'm just going to pump it back up to 40 real quick for the heck of it, even though 20 is probably a better deal. I don't know, I just want to. 20 I get a better, at 40 I get a better accurate, more accurate shader, that's for sure, with the same computation here. At 30 it's really good. At 20 you notice we lose some of the specular on this. Check it out. It's still there, it's just not as, well, it's not even hardly there. I guess it is kind of. More like Lambert. Yeah, pretty much 30 looks like it's about as low as it goes, man. Alright. So there you go. Looks like you can't really go much below 30 on this particular one. Alright, so there is our Phong Vertex shader with textures applied. Okay. Now let's move on, going a little further here. Let's look at our Phong Vertex shader without textures. Alright. This is what you're going to do is you're going to go up to Create Effect. Alright. You're going to choose CGFX here again, as always. Choose empty, name it what? PhongVS underscore PS dot, well, just that right there, and then it'll be .cgfx, of course. You're going to say next, it'll automatically pop in the name for that for you, and then you say finish, and it comes up. Great. Awesome. And of course, you're going to need to copy your code from this one here in order to create the next one. Now, this one's going to vary somewhat here. We really are going to kind of break the mold with this one. We're going to take a different approach to this than we did before, and it's required, pretty much is needed. So I went ahead and applied this shader so you can see what it looks like, and you can see the difference. Okay, so let me show this real quick. You can see the difference pretty strongly between a vertex versus a, sorry, this is our vertex one. See how bumpy that is? If you can't, I'll zoom in. See how poor quality that light is there? You can actually see the clunkiness to the actual specular, right? Now when I go back over here to the and it would look really clean if we had a tremendous number of points in our model, and that might be doable later on here in next gen when we're pushing like 600 million polys with tessellation shader. Then this might not be a problem anymore. But if you want it really smooth, then you just go ahead and hit the pixel shader. And since this is being updated per pixel on the surface, we get really nice highlights and really clean, smooth highlight surface. It looks very realistic, and this is what's being used currently on games for the most part. Although, like I said, with next gen, the Vertex shader may actually become very usable just with the tessellation shading happening, and then it might be a great idea to use that because you're gonna have like tremendous number of points in the model up close, and therefore you might just get perfect speculars on it just like this, right here from what we're getting with our pixel shader, and maybe have it cost us less in computations, and you can't even tell the difference, in which case that's awesome. So then this older technique might come back to be useful again on newer next gen stuff. Who knows? You'd have to play around with it, test it to see what you get for the best results, because if you can save some performance on that and get comparable results, then hey, use the one that uses less, is less computationally intensive, so that way you can push your graphics as far as possible. Okay, with that said, moving on. This is our shader though. It does look great, and it is awesome in many respects. Okay, so all this stuff is the same from before, right up here. So let's go right down here to Tweakable Parameters. Tweakable Parameters. Alright, so we have our point lamp 0 here, and we have a float 3 here, and this all stays the same for our lamp position. Our ambient light here, you'll notice all this is the same. The same. Sound like a broken record. The same. Alright, all the way down to this point here. Now, of course, we don't have the texture here. Why don't we have the texture? Because obviously this is not textured. This is just the pixel shader alone without textures, and it really shows up very apparent on this without the texture. I mean, it just shows up night and day on the surface here. So it looks great. Okay, so here we have our strut VSN. So we're still doing our N here, and this hasn't changed here. It's still going to be a position with a float 3 here, colon position, all caps here, semicolon. Same thing here, float 4, normal, colon, normal, semicolon here. This is open curly brace, close curly brace, semicolon here. And then we have our struct VS out for our vertex shader out here, open curly brace here. We got our float 4 here, position, colon, position, all caps, semicolon. And then we have our float 3 here, LW. I called it LW for world space coordinates here for my L light direction vector, and then my normal is going to be done in world coordinates here, so I did NW for that, and I did VW for my view here in world coordinate space also. So there's our view direction vector here, and these each one is going to be text coordinate, a different texture coordinate space, starting with 0 here for our LW here for our text coord 0, and then text coord 1 here for our normal in world space, and then text coord 2 here for our view in text coord view in world space here for text coord 2. Alright, so here we go. Struct FS out here, open curly brace, float 4, color, colon, color, semicolon here, and that's all caps color here. Close curly brace and semicolon, nothing new. Same as before. I put these, I know I reordered the code a bit, okay? I did it on purpose to make it easier to reference it. So now when I need to check data types to see if something's off or whatever, I can easily check it just by moving up here between our shaders functions here. And I thought that was just a better layout of the code to make it easier to move back and forth between our main functions and that of the actual data types. So that way it causes less confusion and makes it easier, faster access time when programming and debugging. So I did that on purpose for more strategic layout for code for development and coding purposes here for debugging. For debugging. All right. So here we have our VS out here. So it's vertex shader out. All right. That's our data type. So that struct I just showed you a second ago. And then we have with the different texture coordinate spaces, right? Texture coordinate 1, 0, 1, 2. All right. So main VS here's the name of our function as always. This hasn't changed. Open parentheses VS in here, all caps IN, close parentheses, open curly brace, and here we go. Alright, so same as before. VS out here, semicolon, this hasn't changed. This is the same too. Both of these are the same. This is the same here, only we're doing it now W here. And this is going to be a multiplication, of course, with our world inverse transpose coordinate matrix. World inverse transpose matrix, and then we have our IN here for N value coming in. This is normal from our actual 3D program for this model. All right, for this particular point face on the model. All right, so here we go, X, Y, Z here for our coordinate system here. Sorry, great. So we're doing that multiplication to get into world space coordinates, and it's going out as the normal in world space. It's going into the texture coordinate space here for that. Awesome, and I believe that's texture coordinate space 0, I think. Let me see. It is, no, it's 1. It's the texture coordinate 1 here. L is 0. Doesn't matter. You can switch it around whatever you want. All right, so out.lw, just as long as it matches up. Well, it will match up because we're going to pass it in, so it doesn't really matter. You can switch it up to whatever you want right there, and it changes it everywhere. All right, so out.lw, I did it on purpose to make it easier, so that way you don't have to try to get things match up. Fewer chances for errors when you're going back and changing things around. So that way it helps with debugging and causes less errors. So coded out for that particular reason in that particular layout in that particular way. All right, so out all caps here .lw equals in parentheses lamp 0 position, or is basically the position of our light, minus PW. Now remember, PW is our world space coordinates for that particular point on the model. Awesome. Close parentheses, semicolon. And you can see again, we are doing our point calculations. So you want to do all your point calculations where? You want to do them in the vertex shader. Why the vertex shader? Because it's the vertices, it's the points. So we need to do our point calculations over here in our vertex shader. And then we need to do as many of our mathematical calculations here that don't involve the points to be done per pixel so that we get the smoothest result. And that's what we're going to be doing over here with our normalizing them. Okay, good. So let's move on here. So out.vw equals normalize float 3 here, and then view at ix here, which is our inverse view, and we're doing this for our transforms, our tx here. So this is getting the tx value here for the w. This is going to get the ty here for this one, and it's going to be the tz here for the view here, inverse view. And I just showed that earlier. Just quick refresher right here. Here it is. TX, TY, TZ. I've gone over it many times. Go back and look at the video if you don't remember. minus PW here, or point in world space here. Alright, so out.position equals mul for multiply, MUL, and then in parentheses world view projection comma PO here, because remember PO is going to be what? It's going to be our object space here for our point position on the model. Awesome. Okay, so with that, now we're going to say return out, semicolon, open and close curly brace. Now come over here to our fragment shader. FS out is going to be our output, which is just the what color. That's right. That's the only thing that's in that struct. If you remember right, and don't worry, there's a reason why we put it up here close by, so we can easily get to it. There it is. All right, awesome. Okay, so we have our main PS here for our pixel shader, and this is the main function for handling this. Our VS out, which was the thing we just finished passing out of our Vertex shader, is now getting passed into what? Our pixel shader. Yes, and then we're calling it IN here, all caps. Close parentheses. Open curly brace. FS out, out dot semicolon. Now this is nothing new here. We've been doing this for a while. Okay, now this is new. Float 3 ln normalized L here equals normalized in dot lw close parentheses semicolon, and so this is coming in through what? The texture coordinate space, and it's coming in with all three floats, and it's basically lets us pass in these positions. Now you may have noticed something else here. This V was normalized. The reason why is because after this multiplication operation occurred, it would not fit inside the texture coordinate space. The values wouldn't. So you need to normalize those to pass that in. So here we're going to actually normalize this value, which will be faster because we're doing this per vertex anyways, right? So it means we're calculating this fewer times, which means we're going to get a speed up from this. At the same time, though, we're going to have to do it anyways because we're going to have to pass it through our coordinate space, so in our texture coordinates. So you know that's basically has to be normalized right here, and it's the only one that's getting normalized. But don't forget, V is already normalized. All right, you could even call it VN if you wanted. I don't know. All right, so we have our float 3 here in where N is our what? Our normal that's been normalized. So here we normalize our in.nw. So we're normalizing our world space normal coordinate, our world space normal vector. Let's put it that way, and then close parentheses here, which will calculate that, and then we'll have a normalized normal. And don't forget, your normal is what? It is the the vector going straight up, and your L is going towards your light here. Of course, it's your vector to your light. Don't forget that. V is to your view, and R is your reflectance vector. That's correct. All right. So float 3 here, Rn. Remember, this is our reflectance vector normalized. We're going to normalize it here with this normalized function, and then we're going to say in dot VW. Remember, what is VW? VW is our view, or our eye, or our camera, however you want to call it, vector here, pointing to that. Okay, so that's dot VW here. Now, the VW here doesn't have to be normalized in and of itself. It is already normalized. It was done back over here in our Vertex shader. That is why we're not wasting an extra calculation on this per pixel. That saves us a lot of computations by doing that. So we just made it a little bit more efficient and streamlined the shader a little more to make it run a little faster. All right, plus here ln. Now our ln here is normalized. You know, its normalized operation takes a little bit of time to calculate. So the fewer of these normalizes I'm running here, the faster the thing's going to run. So here we go. ln here is normalized for our vector to our light. And since both of these are normalized, it's fine to now add these together. Once I add these together, they will be too big to for the magnitude. Could end up being, you know, magnitude could be 2 instead of 1. Magnitude has to be 1. The length of the vector has to be 1, not 2. Or for a vector to be a unit vector or a normalized vector, right? So to give us nothing but direction. So therefore, after we add these two values together, it has to be normalized to get it back into a 0 to 1 value here for each different aspect part for x, y, and z of this vector here for our reflectance vector. Awesome. Okay, so float 4 here, lit capital V here equals lit function here, open parentheses, dot product here of our light normalized light vector, sorry, and then our normalized normal vector here. And then we're going to take the dot product of our, and this is our diffuse calculation right here. This is the diffuse calculation. This is going to be our, what? Our specular calculation. That's correct. All right. And so we're going to do our reflectance vector that's been normalized here by our normal vector that's been normalized. And it's going to go to the power of the specular power, which is over here, which determines the look of our specular. Now this is cool. Now you can really see that when you push this down further on this particular setup here with our specular power, it does make the surface look a lot shinier. Look at that. It just looks really shiny. Like almost like a wet surface, right? But if I go ahead and pull this down, the surface starts to gain like it has more pocked and marked little edges here. If you take like a microscope to a surface, you'll see like a surface is all scraped up and everything at a lower level where it has a lot of edges. That's what catches the light and it's going to cause a larger specular like that, which means it's going to be less shiny. And you can see on a model like this is less shiny. This does not look as shiny as the other one, whereas the other one almost looks like wet, shiny, almost like liquid paint almost. It's so shiny on the setup here. So, you know, depending on how shiny the object is, you know, depends on your specular power here. So that's what's being affected there. And again, our specular power is what it is, our value here that's getting passed in right here, spec power, and that is applying to this particular artist's controllable mechanism here with our slider. Alright, so with that calculates it, returns what? Our y here, it's going to return a 4 float here, and the y value and the z value are the two ones we're interested in, because y is the diffuse and z is the specular, and of course our x is always 1, so we don't care on this one. I hope you remember that. We're going to remove that because it's going to do what? It's going to speed up our calculation if we do. That's one more multiplication that we don't have to do on the 3D card, so therefore it's going to be faster if we remove that. Okay, great. And again, we're going to do our ka.rgb. Now, our ka is our what? Our ambient value here for this artistically controllable. This one right here. And you're not seeing it too much because we haven't done what? We haven't turned up our ambient shadow to have that be affected more. So now if I do this color value variation here, you can see it happening more so. More of an effect. Of course, if I go in here and change my diffuse, it's going to be significant. That kind of looks cool. We'll go with that for now. Alright. So, with that, let's have a look here. So, where am I? Here I am. Alright, so we have our KA, this is going to be our ambient color, and then we have our global ambient color, which I just manipulated in order to reduce our shadow here. This is our ambient shadow value here. Again, you could call this ambient light intensity or something like that, or I don't know. That'd be a good name for it, really. And it's fine, you know, you can sit there and play around with this, and then the artist would know exactly what it is that they need to do. Okay, with that, great. So we're going to have our float 3 here, diffuse equals lit v.y times lamp 0 color here, semicolon. So we're going to say our diffuse color from our calculation up here for our diffuse intensity, if you will, for this particular point on the model. In this case, it's not going to be a point anymore. We're talking about a pixel. So this particular uncomputed pixel on the model is being computed here in this value here for the calculation, times the color of the light. Alright, over here, same thing. Because we are doing this in the pixel shader here, and it's going to be a different setup here for the specular also. So we're doing this for the diffuse color intensity for that particular pixel on the surface, and then also the pixel for the specular on the surface here, which is our lit v.z here, times our ks, which is our specular artistic controllable color value here. Awesome. And you can see that you can actually colorize and drive that. Great. And we're going to multiply that also times the light color, the color of the light here. Great. So that when someone changes the color of light, it will also change our specular. Nice. Okay. And then we're going to say out.color equals float 4 here, open parentheses specular plus open parentheses kd.rgb times open parentheses diffuse plus ambient close parentheses comma 1.0f close parentheses semicolon. Alright, now why are we doing this? Okay, well, if you remember right, we've seen this kind of before already. We're doing our specular added to our KD value here, because our diffuse value, times our diffuse intensity plus our ambient diffuse intensity. Alright, not ambient diffuse, our ambient intensity here. our ambient value. And by doing this, we end up with our overall color here. Return out, which is going to reply out what the color. Yes. Close curly brace here. And now we're down to the home stretch for this one. Technique here, space technique 0, close curly brace, and then we have pass here P0, open curly brace, def test enabled equals true, semicolon, just as before. This is all the same, it hasn't changed. Def mask equals true, semicolon, cold face enabled equals false, semicolon, enable blend enabled equals false, semicolon, def func equals less than or equal to, L equal is that, you know, semicolon, and then vertex program equals compile VP40 main VS open close parentheses semicolon. Now it takes a more powerful profile to handle this. You have to have hardware that can actually handle this. Fragment program equals compile FP40 main PS open close parentheses semicolon. We may not be able to have 30 handle this one. I wouldn't be surprised if it can't. It doesn't, I figured. Only 40 it can handle this. Okay, I'm sorry. I did it again. And that's a P I deleted again. I'm getting good at that. Alright. Okay, so 30 seems to handle it. Awesome. I can guarantee you 20 will not. There's no way on earth 20 will, because 20 can't handle a vertex. There's no way it's going to handle pixel, because pixel is even harder to handle for hardware than the vertex is. As long as the hardware can keep up with this, awesome. This is the best way to go. It's going to give you the best result. As you can see, it gives you beautiful speculars on your surface, and it just gives you a wonderful looking light model and gives you a really nice look to everything. And this is current gen, next gen programming right now in games. They're using it currently. Alright, so with that, we have a closing curly brace, and we're done with that one. The next one we have to do is our texture one. So this is our Phong texture shader here, and what you're going to do is you're going to take your other shader here we just did, which is our Phong VS underscore PS shader here, and you're going to copy all this code from here, and you're going to go up here to your create effect. You're going to choose our CGFX here, say next, choose empty, and then name it what? You're going to name it PhongTextureVS underscore PS, like this. You're going to say next and then finish, and it's automatically going to fill in the name from the name you put in here, right here. Okay, awesome. And again, it's .cgfx for it. Great. So everything's the same for the most part, except for a few things that we're going to need to add here for this. Okay, so one of the few things we have to add is scrolling on down, and this is great because it puts everything in the same area by having this code reordered like this. Alright, so one of the things we're going to have to do is going to be the texture. So scrolling on down here, you can see nothing has changed all the way through here. All this is the same. Nothing's changed since the last shader, which is Phong VS underscore PS. Okay, now we're going to add this again. Copy and paste it from your Phong texture one over here. So come over here, select all this right here, starting from our color and texture comment, all the way down to our sampler 2D color sampler one right here. Control C, go over here to our Phong one, and simply place in your cursor here and hit Control V to paste in that code to have it right there. Awesome. That's all you had to do to get that part. Last part of this practically. You're going to now say float 4 here, UV colon text chord 0 semicolon. Now you need to add this into your VSN one, right? Because this is our vertex shader, and this is for the incoming, for the values coming into our variable in our struct for our data type here. And then for our VS out here, we're going to also add UV text chord 0. That means that we need to reorder these other ones here to text chord 1 for our LW, or for our light vector and world coordinate space. For our normal world coordinate space here, we're going to set that to 2 for our texture coordinate, and then for our view world space coordinate setup here, we're going to we're going to set that to our text chord 3 space, text chord 3 space. So now we have 4 texture chord spaces, text coordinate spaces, texture coordinate spaces, however you want to say it. Lots of different ways to say it. Okay, struct fs out here for our fragment shader out. Open curly brace, float 4, color, colon, color, same thing as before, semicolon, close curly brace, semicolon. Nothing's changed. Alright. This is all the same. The whole thing's the same, except for this one spot right here. This is the only time it changed. out.uv equals in.uv.xy here, semicolon. So alright, it's going to pass out our UVs here for that. Important. Everything else stays the same. Okay, as far as this goes here, the only thing you go and you add to this is this one right here, practically, and then we have to do something here too. But basically we have our float 3 here, and then diffuse color equals text 2D, capital D there, open parentheses color sampler, right, because that's the name of our color sampler, comma in here dot UV for our UVs coming in to it, close parentheses dot RGB, alright, semicolon. And then over here for our diffuse color, we're going to do our diffuse color times our KD. That's it. Everything else is the same, and you are done. And that will give you a overall texture that can be applied to the surface of this model, along with the Phong, Vertex and pixel shading here. But basically, our lighting algorithms being done with our pixel shader here, and it's giving us a really nice, smooth, clean appearance to it, and it's beautiful. So that's great, and that's what you want. And of course, you can add another texture here if you need to. All right. That was a lot. That was 3 shaders in one video. So we were moving very quickly, but this was stuff we'd already covered a lot of in the previous video, so we didn't have to cover it over and over again. But that covers all that, and now you are set up with all 4 Phong shader implementations here, going from just regular colors to actual textures involved too. And then you can mix this up, add different textures to like specular, or you could do, you could do any of the stuff you learned from previous with lerps and, swizzling and any of the other type of mathematical operations I showed in the previous videos also apply to this with our light model, but you can sit there and mix things up and apply it to different channels and different operations versus diffuse versus ambient versus the specular, etc., 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 and manipulate these things in all different ways. So very powerful, very cool, and there's a lot you can do with this. Have fun, play around with some of the stuff you learned from before with these new techniques, the light shading here models, the light models here. With that covers CG light models for Phong shading here. I'm Nate Nestler, and this is for Hyperactive Studios. Thank you very much for watching.